Recording is rolling. It's Thursday, September 8th. We're doing some projectile stuff. So you what I wanted to do this week that we won't quite have time to get to is a projectile lab. So I'll just push this off next week. But just to show you a little bit of setup so you have to be able to think about it. Guys, this launcher right here. So there's a little yellow ball. Actually, it's right there down that desk. You can push it in here. The thing will go like click, click. Right. Like you're loaded a cannonball, and you pull a string, fire. And look, you can change the direction. This ball will hang down. Oh, look, there's a built-in protractor right here, so you can see what angle you're aiming it at. It'll go some distance. So there's a few different lab questions that I could ask. I'll come up with some up for you guys, but we'll have to push that off to next week, though. Right. But how about the rest of this week? So I want to do some graphs with you guys today. With some graphs. I want to stretch your guys' imagination a little bit and show you guys the range formula and how to solve for an optimal angle to send something the furthest horizontal displacement. Okay, and then we'll break out this page and just I'll solve as many with you guys as I can till the end of class. Remember, this page I'm picking up from you guys by Monday. This is your guys' projectile homework. So far in class, we've done this example and this example. Yesterday, hopefully you guys were able to work with each other, knock out some of those, and I'll do some more with you guys today. Okay. Oh, linear motion quizzes. These were doing a few days back. If you turned in yours already, then it's graded and your grade is in the grade book. If you haven't turned that in yet, get it to me real soon because you get those grades in and get those back to you guys. Today is the last day of interim 1. We are 1/8 of the way through the entire school year. Teachers' grades are due here in the next few days, so gotta post grades and yeah, grades are going in the grade book. All right, well, let's get rolling. So projectile graphs. I want to look at graphs related to this scenario right here. Right. Good. There are two main classic scenarios that we're going to focus on. There's this one and this one, right? It might be a can edge of a cliff horizontal, or you can have a can down the ground pitched up at some angle, right? We'll look at this one in a few minutes, but let's start with the can on the cliff. Just edge horizontal, real straightforward, just horizontal. That type path, right? Here's the vertex of a parabola, okay? And I want to have you guys draw 3 graphs related to this motions of that cannonball. So here's your scenario. Cannon, if you guys are keeping notes, right? Scenario with you guys, aimed horizontally at edge of cliff, just like that picture you just saw. I'm going to throw some definitions on here. Let's define down to be the positive vertical direction, right? And so gravity is pulling in the positive direction, right? As the cannonball falls, it's falling in the positive vertical direction. Okay. Also, I'm going to define the top of the cliff as 0.0, like the 0 meter mark. Okay, so that as the cannonball, well, it's going into a projectile path. It's going to the side and down at the same time. Let's say to the right is the positive horizontal direction, and if down is the positive vertical direction. If it starts at 0.0, it's only going to fall into positive territory. Get that? Okay, here's 0.0 up here. Right, then here's further positive as you get closer to right here. All right. So what graphs I got lined up for you guys? I'm going to do 3 graphs, and I can fit them pretty well on one page, so I split my page into 3. Like some European flags. Set up some axes. For just to help you guys out a little bit here, these are all going to be first quadrant graphs. All the numbers are going to be positive, just the way I'm going to set this up. Okay. Of course, not universally true. Could ask a question where there's some negative numbers involved, but not on this one. Okay, so one graph, let's go. Let's say the vertical displacement. I'll say h, like height, like what's the height change as a function of time ticking along. So height in meters as a function of time ticking along in seconds. Okay. In fact, I'll throw one point on here already. At time 0, let's call that position 0, which is like up here, right? Okay. So I'll throw 0, 0 on the board just to get you guys started. Okay. Then as time ticks along, tick, tick, tick. What's the height drop going to be? right? Remember, the further it falls, that's a more positive height change, right? The way this is defined. Oh, after that, let's do velocity in the vertical direction, just the vertical component of velocity. That's what v sub y is, as a function of time. So how fast is it moving in vertically, just strictly vertically, meters per second, as time is ticking along in seconds. And last graph, let's look at it as the horizontal component of velocity as a function of time. The meters per second, and time is in seconds. Okay. Yeah, there we go. And so those three graphs. And so you guys know that you have the premise written like I do at the top. You guys have three different graphs set up. If it takes more than one paper, it could be a good idea that you can fit all mine on that page right there. Okay. See if you can stay a step ahead of me, just like normal. If you guys can draw the graphs before I draw them, then that's a really good indication you know what's going on in this class. So trying to give you guys a head start here. Head start. All right, so my guys are talking up, drawing those axes. Think about those. If you draw the graph and you get it wrong, you just erase it and go back and draw it later. Okay. Remember, this is the scenario we're looking at. Okay, and then have you guys draw three graphs. All right, you guys ready to start plotting these down? What shape did you guys come up with for height fallen as a function of time? What shape is that? Not sure. Here, but let's get some numbers. I bet if we plot some points, we can just connect some dots and make a shape. So let's let it fall for like 3 seconds. So let's take like a 3-second tall cliff, drop the ball. Right? Or, hey, how about this? Would this be true? If you blasted a cannonball horizontally and you drop a cannonball off the edge at the same time, are they gonna hit the ground at the same time? Yeah. Does that mean they have the exact same vertical motion? Sure does. Right? Now they have different horizontal motion, but they have the exact same vertical motion, don't they? Right? Ooh, and if that's true, then do you remember how far does would the cannonball fall in 1 second? And it's not 10 meters, it's. Do you guys remember a formula that goes like this? Right, you guys remember that? Right. That's a shortened version of this first kinematic equation, relates displacement and time for an accelerating situation. Okay. Instead of x for some general displacement, I'm saying like a height drop. Can I say v naught in the y direction specifically is 0? Because yes, when this cannonball is blasted horizontally, how fast is the cannonball leaving the barrel vertically, like up and down? Yeah, 0. That number is 0. That's why it's okay for this to be 0 and that term goes away. And then instead of some generic acceleration, I'm saying acceleration specifically due to gravity. That's the g, right? Yeah, right. 10 meters per second squared. So if you pop in 1 second, 1 squared times 10 divided by 2, that's a height drop of what? 5 meters. So after 1 second, hasn't it fallen 5 meters? Right, I've got the unit meters embedded in the axis. 5 meters. How about after 2 seconds? How far did it fall? See, what's 2 squared? Times 10 divided by 2? 20. Oh yeah. 20 meters. How about 3 seconds? How far did it fall vertically? 45, which is kind of here-ish. 45. Pretty close. Okay. Oh, what shape is that? That's a parabola, right? So displacement as a function of time, when you're accelerating, yeah, you always get parabolas. All right. Okay, all good? Okay. You guys got, oh yeah, go ahead. Oh yeah. All right, how about the next one? The vertical component of velocity is a function of time. In fact, we've already mentioned what it is at time 0. Here, let's go over that again. When you blast the cannonball really fast horizontally, vertically speaking, how fast is it moving leaving the cannon? 0. So at time 0, that's say leaving the cannon, isn't how velocity 0 meters per second? That'd be that point right there, right? Okay. So there are some times, 1, 2, 3 seconds. After 1 second, it's picked up vertically to a speed of what? There you go, 10 meters per second. Right? How about after 2 seconds? 20? How about after 3 seconds? 30? Ooh, good call. You guys are on. Okay. And that's because you guys are saying velocity in the y direction is just gt, right? Which is a simplified version of this guy, right? So here, this is 0 for this scenario. It is anyway. Okay. G times t. Okay. Okay. So 10 times 1, 10 times 2, 10 times 3. Okay. Oh, and isn't that a direct relationship then between velocity and time? Boom, straight line. Okay. Good so far? Okay, so now these first two graphs are both related to strictly the vertical motion. That has nothing to do with the blast speed from the cannon. Right? The blast speed could be anything, and those graphs would be the same, wouldn't they? Right? One is how far is it falling, one is how fast is it going vertically. Right? Now let's switch over to horizontal. Right? Horizontal motion. Suppose this cannon blasted at like 40 meters per second, just to come up with a number. Let's say it's like 40 meters per second. So at time 0, it would be going that fast, right? Time 0 is 40 meters per second, horizontally, right? How about 1 second later? How fast is it going horizontally? I mean, gravity only pulls vertically, right? Does gravity pull horizontally? No. So let's see, there's no horizontal force from gravity. We're still ignoring air drag. So is there any reason for it to change what it's doing? No. So after 1 second, it's still moving 40 meters per second. How about the next second? Still 40? Yeah, it'll go 40 meters per second horizontally, as long as it's in free fall, right? All the way to the point where it crashes in the ground. Flat line, right? Doesn't change. Right? You guys remember that? Oh, actually, I got a sort of a picture of that right here. We're doing a Kahoot with my conceptual students. I do want to do that with you guys sometime with it, but here, actually, here's the problem that we're doing, right? We're just doing this to split half like that. Right? So you blast out this cannonball. Is it speeding up as it's falling? Yeah, right. But then if you look at components, see how the horizontal component stays the same all the way across, right? That's what we just did, right? It's the same value. Right? You guys get that? All right. What I got next? You guys ready for our next activity? Next one. All right. So let me forewarn you guys. I'm going to show you guys something that's going to stretch your imagination a little bit. What I'm about to show you guys, I'm not going to test you on, but I do want you to see. It's like, okay, yeah, I can kind of see how this would fit together. Go right. So we're going to switch models. We're going to go to this one. We got a cannon on a flat plane. We're going to blast, and it's going to land some distance x away from the cannon. Right? Is that? Right. Or you know what? I could change the story too. How about this? You get with your friends and let's have a baseball throwing contest. And the question is, who can throw the baseball the furthest distance x? Okay. Now you can't really control your maximum throwing speed. You know, warm up and the whole deal, right? You can throw as fast as you can throw. What you can control is the angles that you throw the ball at. Isn't that true? Right. Right. So I might have a question like, hey, I wonder what is the optimal angle for the ball to go the furthest distance? Let's do some thought experiments here. Like if you took this angle that I've labeled 53 degrees all the way to 0, wouldn't the ball just like immediately hit the ground, like go nowhere? Okay, so that wouldn't be any good. So you ramp it up a little bit. Let's say 10 degrees. Ooh, now it's further. 20 degrees. Oh, now it's even further. And you keep ramping up the angle. It goes further, 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 until at some point it's gonna max out the distance and you make the angle too steep and actually starts coming back, right? And how about this? 90 degrees straight up. What happens? And then it lands back and like destroys the cannon, right? The displacement would be 0, right? So I wonder what that optimal angle is. Does anybody have a guess what it is? Anybody have a guess? 45? Right? We got a call for 45 degrees. That seems like it would make sense, right? Maybe 45, right? How can we find out? Right, so this is going to take 2 parts. First, I have to come up with a general formula to relate this horizontal displacement x called the range, this range, to some generic angle theta, right? Once I get that formula, then I'll show you how you can use that formula to optimize. Right. All right, so here we go. Right. You guys ready for this adventure? Right. This question involves this whole packet right here. Right, so take your this packet. Here's our setup, right? Now, the first thing you do is you split this blast bead, which I'm just calling generic V, into components. Here's V cosine theta, V sine theta, playing off that horizontal angle theta, right? Right, okay, see that? Right, I'm gonna go through this kind of fast, but I'm recording all this too, you can see it on the video, right? Right, and then how far it goes, isn't that just the horizontal component of velocity times time? X equals V sub X times T, right? But the V sub X, isn't that the blast speed times cosine theta? Right. Now, here's the thing, that angle theta and that T are not independent of each other. And it kind of makes sense if you think about some examples. Like if the angle is really small, like 5-10 degrees, the time in the air is also very small. The closer you get that angle to 90 degrees, that will keep increasing the amount of time. In fact, there's kind of a trade-off, right? Because the greater the angle, the less the horizontal component of velocity, but the greater the time it's in the air. So some kind of trade-off going on. Here's what I'm trying to get at. I can get this T in terms of this theta, and then I'll have just some formula X only in terms of the angle theta, right? So that if you know the angle you pitch us at, you know how fast you can throw it, you can know how far it's going to go, right? All right. So here's just one of several ways to. There are lots of ways to get there. Here's one way. Take that second kinematic formula. You guys remember this one, right? Isn't it true that if as long as you're on a flat plane, however fast it's blasted up, it's going to come down same speed, opposite direction, right? Solve for do some algebra switcheroo. Solve for T, and T in terms of theta ends up being this, right? So here's what this says. If you know the blast speed of the cannon, and you know the gravity field of the planet, and you know the angle you pitched at, you can at least figure out how much time it's going to be there, how many seconds. Okay. Right. Again, I'm not going to test you guys on any of this. I just want you to see it. Say, oh, okay. I can kind of see like big picture forward for the trees how this would work, right? Okay. All right. Now, what are we going to do with that? So I'm going to take this dash outline expression. I'm going to do a little substitution. So we're back to this x equals v sub x t. Now we already substituted out the v sub x with v cosine theta, right? Loss v cosine theta. Now this t, I'm going to substitute in that whole expression that I just showed you on the page, right? Switch some stuff around. It could look like this, right? Now, I don't know if you guys might remember from a pre-calc or a trig class. Do you guys remember things like double angle identity? Double angle identity. Oh yeah. Okay. All right. That one winner was like. So sine of 2 theta is the same thing as 2 times sine theta cosine theta. When would you ever use that? Oh, here. You would use that here. Okay. So you can simplify this like this, and then you can get what's called the range formula. Right. In fact, if you go to Google or Wikipedia and type in range formula, this will pop up. Right. So I derived up to this point. Right. Say someday you're but here let's just use baseball example. Right. I was going to use an artillery example, but I guess you could do that too. Right. Baseball example. How far can I throw the baseball? Well, how fast can I throw? What's the gravity field of the planet? What angle do I pitch it at? You see, just pop. And you can figure out how far you can throw the ball. Right? You get that? Right? Or you could transfer. You could solve for anything. Right? If you say you want to know, I wonder how fast I can throw the ball. Well, I know what angle I threw it at. I know Earth gravity, and I know how far it went. So I could solve for v in principle. Right? You guys see? Like if you know any 3 of these, you could solve for the 4th one. Right? That? Right. Okay. Now. Great, so we got ourselves a range formula. We got how far is a function of the throwing angle, right, or the blast angle. But how are we going to answer the question, what is the optimal angle to maximize x? Right. Whenever you get a question like that, what is some optimal value to maximize or minimize something, like you're trying to optimize something, right? That is a calculus question. And I'll tell you guys why it's a calculus question. Because calculus is about rates of change, and the rate change of something goes to 0 for an optimal value. Let me show you guys why. Okay, so here we go. Here we got the range formula right here. And on a graph, it'll look like this. So x is a function of theta. Remember, if you blast it 0 degrees, it just immediately hits the ground, it goes nowhere. If you shoot it straight up at 90 degrees, it just also lands exactly where it started, which would be nowhere, right? But then anywhere in the middle, it's gonna like go further at some point, and then start coming back, right? That's what this looks like. This might look like a parabola. It's actually part of a sine curve. Anyway, that's not. And what I'm trying to get at is, if I want to maximize the distance that it goes, what angle would that be at? What optimal angle? Right. You guys can probably just see at a glance it's gonna be 45 degrees, right? So good call on 45 degrees. It's halfway between these two, right? But let's do the formal math, right? So do you guys see how I can hold my roller flush to this curve and it starts out really steep, and then it gets less steep, and then the slope at the top is 0, and then it goes negative. You guys see that? Right. Whenever the slope of a curve is 0, like it is right at the top here, that's to say, the rate change is 0. That means you're optimizing something. In this case, you're maximizing x for some optimal angle theta, right? Is it? Right. So if you guys take calculus one day, then you'll know how to take the rate change of this range formula, and it looks like this: rate change of the range with respect to the angle. So don't worry about the calculus mechanics; it just ends up being this, right? I just want you guys to see big picture, like, oh, okay, yeah, I can see how that would work in principle, right? Right. All right. So now, if you take this rate change expression and you set it equal to 0, that would be able to pinpoint this location, wouldn't it? Okay, so that, right. So I'm going to take this expression and set it equal to 0. Right, ba-bam, right there. Okay. Now, the v and the g, those are constant values. You can throw whatever speed you can throw. Gravity is whatever it is. So really care about this cosine bit being 0. So set the cosine equal to 0. Now, do you guys remember on a unit circle where cosine is equal to 0? At 90 degrees and 270 degrees. I don't care about the 270, I care about the 90. Okay? Right. Well, you could do the other one too, but let's just focus on the 90, right? So that's the double angle is equal to 90 degrees. Divide both sides by 2. Oh, there's the answer, 45 degrees. That's your optimal angle to maximize that. Okay. All right. You guys get that? That was a fun little adventure. Yeah. Mostly I care about that you see some big picture ideas there. Okay, yeah. The big picture, how kind of that would work. All right. Are we ready for, yeah, we're ready to solve some more projectiles. More projectiles. All right, so I know we did a couple of these in class together already. Hopefully you guys were helping each other out yesterday when the substitute was here. All right, before I just start solving these, how much time we got? We got till 37 after. All right, we're doing all right. Does anybody have a request for a specific scenario? Yeah, which one do you want? This one right here? All right, let's take a look at this scenario on the bottom left. See what we got here. Now, remember how these are organized. The left 3 scenarios all look like this cannon on this cliff. And these 3 right scenarios are all some version of this. Okay, all right. So we're doing a cannon on the cliff. Okay, guys, get cannon on the cliff. All right, let's check this out. Cannon fires a cannonball horizontally at some given speed, which would also be the horizontal component of velocity. Okay. Off a cliff of given height. Oh, okay, so I told you the height of the cliff. Right. Ooh, on an alien planet. Ooh, alien planet. That means we don't know the gravity rate. We don't know the vertical acceleration. We're gonna find out though. The cannonball lands this horizontal displacement away. Find the free fall acceleration due to gravity and the total speed that the cannonball hits the ground. Okay. Now, the way I gave you these tables, see there's horizontal information here and vertical information here. Guys, look up here. Help me out here. Right. So you can see just at a glance right away that there is enough information you can solve something horizontal. If you know how fast it's going across and how far it lands, you see you can very quickly figure out how much time it was in the air for, right? I want you to know how much time it was in the air for, right? How much time it took to go, let me zoom out here, from here to here. Isn't that the same time to get from here to here? Then you go back to your vertical information and say, oh, well, I know the height of the cliff itself. And if I know how much time it took, I could therefore solve for the acceleration, the gravity. Okay. That's exactly the roadmap we're going to do. So yeah, let's do it. Right. I'm going to start with this horizontal information. Say how far it goes horizontally is the horizontal component of velocity times time, right? And because the cannon is aimed horizontally, this is also the blast speed of the cannon, isn't it? Okay. So we're going to solve for time. Now my numbers go 295 meters across at 190 meters per second was the blast speed. Okay. Oh, I wonder how much time it took to get there. Do you guys see one algebra step, which is divide both sides by 190? So 295 meters per second at 190, or sorry, this is meters. Whoops, meters at 190 meters per second. There we go. All right, let's see what this is. 295 over 190. I'm getting 1.55 seconds. Okay. Now, everybody has different numbers, so my number is different than your numbers, but that's how you would solve that part, right? You guys got that? Alright, so now what's probably a good idea to do is to go in this box and write in 1.55 seconds or whatever your time is, right? Hey, if it takes that much time horizontally, is that the exact same amount of time vertically to fall? It sure is, right? Now, because the cannon was aimed horizontally, what was the initial vertical velocity? 0, right? The cannonball wasn't moving up or down at all, leaving the cannon, right? Which means that I can take that first kinematic equation and just say this: y equals 1/2 gt squared, and do that, right? Right. And you're solving for what is the gravity field on that alien planet. I know how far it fell because that was a given value. I know the height of the cliff. Right. Pretty straightforward to measure that, this many meters. We're saying, what's the gravity field on this alien planet? And I know the fall time because I got that from the horizontal information. I know how far it went and how fast it was going. Therefore, I figured out the time, right? So I'll pop that in right here. Don't forget to square that, right? Can you guys do the algebra and solve for G? You can do that too, right? So G equals, let's say I'm going to take the 21 meters. Got to multiply this 2 over, so times 2. And then divide by this times squared. This many seconds squared. Right? You guys see a little algebra switcheroo? Right? Before I plug and check in the calculator, do you guys see how the units would also be consistent? Meters per second squared describes the gravity field. Okay. So it's 21 times 2 over 1.55 squared. I'm looking at 17.5 meters per second squared. Okay. Seems like a reasonable value. Make sure that's an answer choice. Yep, that's an answer choice. I'm good. All right. Is that working out for you guys too? You guys getting a number on the paper? All right. All right, good deal. Questions so far? All right. The follow-up question to that was, what was the crash speed of the cannonball? Yeah, the total speed of the cannonball is hitting the ground. Right. Now, total speed of the cannonball is hitting the ground. I think we solved one kind of like this before. See this V crash down here? Right. Now let's think about the approach to set that up. Now it's landing on this angle, but it's going across the field and also down at the same time, right? And if you knew what those components were, how fast across and how fast down, could you put that together in a Pythagorean theorem? You get the answer that way? Pythagorean theorem? I bet so. Okay, let's try that. So I know, well, let's get V sub y. V sub y final. Is that V sub y initial? Or V not y, or sometimes reverse this, or plus GT, so some version of that, right? Okay. And this guy is 0. We just talked about that because you aim the cannon horizontally, so that just it's not moving up or down, leaving the cannon barrel. Okay. All right, so I'm looking at 17.5 meters per second squared. Oh, I remember what I was gonna ask you guys. So my planet, you guys see my planet? Would you be really heavy or really light on my planet? Heavy, right? See how this gravity field is like almost twice Earth's gravity? Ooh, you'd have almost twice weight, right? Right. Okay, and what was the fall time? The fall time was this many seconds, right? Okay. So put it all together. Right. You get V final in the y direction. Okay. It's that fast. Okay. Now that's not the total answer yet, but you do need that as the middle step. Okay, so you guys got that? Okay. Okay, now let's piece this together because we're getting really close here. So this cannonball crash land right here. Here's the crash. Right? Here's the vector coming in. Right. And you can split this into components. In fact, we know what the components are. That's how we're going to solve this. Put this all together. Right? We just found out V final in the y direction. Can we take that number? Put it right here. Okay. And all along, we've always known what v sub x is. Because it's the same thing as the cannon speed. It was given to you right here. Right? You guys got that number? Is that all right? It's going this fast across, and it builds up to this speed down. So can you guys do Pythagorean theorem and finish off the whole thing? Okay. So v crash squared is equal to this number squared plus this number squared. There's your Pythagorean theorem. Okay. So last step is to square root both sides. Let's see what that is. In fact, I'm getting a speed that's just a little bit faster than the actual blast speed of the cannon, but which kind of makes sense, right? Because the blast speed is so fast, it only takes up a little bit more speed from falling. So, okay. You guys get that something like that too? You see it, answer choice on your paper looks pretty good. All right, looking out. Okay. Is there another specific request? Or you just want me to pick one? Yeah, which one? 15 through 17. All right, let's do this. Cannonball. Okay, so now we're back to something that's about to look like this right here. Okay, this one right here. Okay. All right, we're on a plane. Cannonball is fired at an unknown speed. Ooh, we don't know the blast speed of this cannon. Oh yeah.
When is this due?
Monday. Okay. An angle of 70 degrees above the horizontal. As a result, the cannonball goes this far horizontally. So I told you how far the cannonball lands. Okay. And I want you to figure out the horizontal vertical components of the blast speed, and therefore the total firing speed of the cannon. In fact, questions 15 and 16 are just to lead into 17. Right? I could have jumped straight to question 17. Right? Oh, and I gave you guys a hint because I typed out this question. I like this question, but then when I was solving it myself, I realized that it's kind of tricky to get the time. So I went ahead and told you guys what the time was. Right? In principle, you could find it yourself, but just be kind of tricky. Okay. So we're gonna play off that hint. All right. How about this? Let's get each of those speeds individually. Would how fast it's going across be equal to how far it went divided by how much time? These are all horizontal values, right? Here's how far it went horizontally. Here's how fast it would have been going horizontally. On my paper it says it went 295 meters. And it did that all in. Okay, now here's where the hint comes in. See in the hint, I told you how much time. Okay. Yes. Mine says this many seconds. Okay. Can you guys get the horizontal component of velocity that way? Okay. Right, you guys get that? All right. Now how about vertical component of velocity? Well, how about this? Could you do y equals v naught in the y direction t minus 1/2 gt squared? Some version of that. Okay. Now I'm using like the full kinematic formula that includes this piece because the cannon is like aimed up at an angle. So there is a vertical component of blast velocity, right? Okay. And I already embedded the negative sign here for gravity, because if you're blasting it kind of upish and gravity's pulling down, there's going to be a sign conflict, right? Okay. Now, if you forgot that you did a plus here, you would still get the right answer. You just get a negative value. And you say, okay, I see, because it would be opposite direction. Okay. So whenever you have this type setup, from beginning to end, isn't the vertical displacement equal to 0? But it explicitly gave that to you anyway. It said y is 0, right? You're just going from the ground back to the ground. This number is 0 meters. We're solving for v naught in the y direction. T was the hint. Here's your this many seconds. 1/2. On this paper, I'm using 9.8 meters per second squared, so I'll just stick with that. Ah, can you guys solve for V naught Y? Okay, guys did it? Let's see what all this fun stuff is. Get it, 137.6 meters. Okay. Okay. Add that over, divide by this many seconds. V naught Y is this many meters per second. Okay. Yeah. Yeah, we will do that too. Yeah, so let me finish this one up and then we will definitely do that. Okay, so now you know how fast across the cannonball is going, and also how fast it was initially going up, leaving the cannon barrel. Right? You guys get that? All right, so let's put this all together. So here's your cannon. Blast. Right. It's going across and also up it, upish. Right. And the numbers went to 55.7 meters per second and 26.0 meters per second, like that. Right. And here's V blast, like the blast speed. You guys get that setup? Right. Of course, the actual path of the ball goes something like that, but I just care about the initial condition. Can you guys do Pythagorean theorem? Right. You guys get that? V blast squared equals V sub x squared plus V naught Y squared. Just pop these numbers in. Take a square root. You have to undo the square by taking a square root, right? So we do square root of this number squared plus this number squared. Oh, we're doing really good on time. We're all right. Okay. So I'm getting this many meters per second for my blast speed. Right. Is that let's ask about that. Oh, that's all three questions, isn't it? All right. So question number 15 is right here. Question number 16 is right here, and question number 17 is putting it all together. Yeah, all right, and I see all those for choices. Okay, so 15, 16, 17. Okay. Okay. You guys good there? Okay. Let me go one more step. Remember, I told you the angle that the cannon was pitched at? If this is all true, then shouldn't I be able to confirm that angle right here? That angle theta? Right. What is that angle theta equal to? Do you guys remember how to get it? Can I do inverse tan of opposite over adjacent? You guys remember doing that a few weeks back in this class? Right. On the printed paper, it says it's 25 degrees. Or well, mine, or is that what mine says? Yeah, 25 degrees. Okay. So I hope this comes out to 25 degrees. Okay. What's inverse tan? Here we go. Inverse tan of 26 divided by 55.7. All right, moment of truth. We're about to find out. 25.02. That'll work. Yeah, 25. 25 degrees. Okay, so it confirmed that. We're all good. All right, so last scenario. A cannon fires a cannonball at a castle wall. All right, so to tell you guys what, it's a modified version of the scenario, but instead of the cannonball hitting the ground, there's going to be a castle wall right here, and the cannonball like crash right about there. Right, you guys got that? Right. So that where it crashes, there's definitely going to be a horizontal displacement F, but there's also going to be a vertical displacement because it doesn't land at ground level. Okay, so we've got both going on. Right. The cannon is horizontal displacement X away from the base of the wall, so we know how far away from the castle we are. And the cannonball strikes vertical displacement Y up the wall. So we look and see where crash lands. Okay, that's so many meters up. Right? It takes some given amount of time T for the cannonball to reach the wall. So somebody brought a stopwatch to this party, which is especially generous because that's both horizontal and vertical information, right? I mean, it's a scalar value, so it could apply to both, right? So that can make those pretty fast to solve. In fact, somebody has a stopwatch. Okay. So 3 questions: find the total firing speed of the cannon. Find the total speed that the cannon hits the wall, like the crash speed. And then finally, the angle above the horizontal that the cannon had been turned. Like, how do we angle the cannon so that all these numbers lock into place and we hit that castle ball exactly where we did? All right, gonna find out. So 18 through 20. Get a picture going. Ground. Cannon. The blast. Okay. It's gonna hit this castle wall right here. There's a castle wall. Pow. Right. Throw some variables here. I know this I could call X. That's the horizontal displacement. This value here I could call Y, the vertical displacement, where it hits up the wall. This blast speed, I mean, at some point, we're gonna have to either break this into components or use the components to figure out what it was. So I could call this V naught in the Y direction. I could call this V sub X. Right? Got that so far? Okay. That's all variables, but we got some numbers on some of these. I know on my page, X is 400 meters. 400 meters, right? I have Y as being 15 meters. Right? I have time is 7 seconds. So let me off over here, do time equals 7 seconds, right? You guys also know gravity is pulling down at, well, on this page it says 9.8 meters per second squared, so that's where we're using. Okay. You guys okay with this setup? Okay. Now, there's actually enough information that you could start with either horizontal or vertical, again, because the fact that we know the time, it makes this a lot easier to solve. Okay. So let's start with horizontal. Why not? Can I say X is equal to V sub X times T? Right? And I know 2 of those things. I know what X is, the horizontal displacement. I went 400 meters. And it got there in 7 seconds. That's the time. Of course, you guys have different numbers than me, but same idea. So can we very quickly figure out what the horizontal component of velocity is? Let's say like how fast it's traveling across the field. Okay. I'm looking at 400 meters and 7 seconds. So that divides out to, that's 57.1 meters per second. Okay. So we go up here and write in equals 57.1 meters per second. Okay. All right, you guys got that? All right. Now, that's not one of the multiple choice answers because we're not quite there yet, but that's an important number to have. Okay. How about V naught Y? Well, I know leaving the cannon, the cannonball was going kind of up-ish, and it eventually ended up 15 meters above where it started. Right? In fact, that I also know how much time this whole thing took. Guys, should I do some version of Y equals V naught Y T minus 1/2 G T squared? I should do that, right? That's a modified version of that first kinematic equation. And I'm saying if you blast kind of up-ish and gravity's pulling down, I've already embedded the negative sign into that G, right? Now, again, if you went into this totally blind or you forgot and put a plus there, you'll still end up with the correct answer. It would just give you a negative value. But I'm saying, okay, up is positive, down is negative. Okay, you guys good? Okay, so, or actually, let me modify what I just said. Okay, because it's 15 meter difference. Okay, actually, you would have to somehow know for this exact setup that gravity is at least opposite direction of where the ball landed. So you would have to, one way or another, have a negative sign attached to the G. Right? You could call it negative 9.8 meters per second squared, but you have to have a negative, otherwise you're not gonna get it right. Okay. V naught Y. Well, we're solving for that because I'd really like to know what that is. This whole thing lasted 7 seconds. It's 1/2 9.8 meters per second squared. 7 seconds being squared. Right. Can you guys do the algebra and solve for V naught Y? Right. So let's see. What is 9.8 by 7 squared? And so V naught Y equals 40. All right, it's gonna look like this. All right, so add that over, then divide by the time. All right, and it gets that. Okay, so where did time go? Did I? All right. So what is the firing speed of the cannon? Guys, since I got about 30 seconds left here. The firing speed. If you know this, and you know this. Can you guys do Pythagorean theorem and get the blast speed? You guys can do that, right? Yeah. Can you guys answer question number 20 by taking the inverse tan between these two? That divided by that inverse tangent. You guys get this. Can you guys figure out final velocity in the y direction and do a very similar Pythagorean process over here? Right? Because here's the crash. The cannonball is moving to the right, and it's also moving down. Is that right? To the right and down. Does the horizontal velocity stay the same all the way across? It does. So this doesn't change all the way across. And if you find VFY, can you do a Pythagorean theorem? Possibly. You know what I can do too? I did cover this one earlier class, so maybe I'll upload two videos to Classroom. Yeah, I might do that. All right, you guys have a great rest of your day.